Hi, everybody. So my name's Amelia. I work at Dstillery. Dstillery is an applied data science and digital advertising company. We are experts at using machine learning to build audiences of devices that we predict will exhibit a certain behavior. So today I'm going to talk about expanding digital survey data. So market research often involves survey panels. So perhaps there's an ice cream brand, and the ice cream brand wants to know its customer's favorite flavor of ice cream. To learn that, they can administer a survey. So they administer a survey, and they ask their customers, what's your favorite flavor of ice cream? And then one way they can act on this survey is they can then determine different advertising messaging to show their customers depending on their responses to the survey. So perhaps in this simple example, they want to show images of chocolate ice cream to their customers that prefer chocolate ice cream, and images of strawberry ice cream to their customers that prefer strawberry ice cream. And so as we work in digital advertising, typically the goal is to show ads to millions of devices. But when you administer a survey, you can only get responses from perhaps thousands of devices at a time. So that's where my company comes in. We can build models. We can predict how a user will respond to a survey. We can then take our models and use them on our device universe. And we can build segments of devices that we predict will respond to a survey in a certain way. So we build segments of devices that we predict will like chocolate ice cream. Then the ice cream brand can serve ads to these devices with images of chocolate ice cream. So it's a simple example, but it's sort of how it works. So how do we build these models? So the data available to us comes from the RTB ecosystem. We ingest 40 billion bid requests a day and from the bid stream. And in these bid requests, we have information such as websites a person has visited, apps a user has engaged with, and locations a person has visited. Today, I'm just going to focus on the models we build using website visitation data. So out of those 40 billion bid requests, we see 1.5 billion website visits daily from a device universe of about 200 million devices. And we collect website visitation history on all the devices in our universe and on including those that responded to a survey. So when we're building models, our data set looks like this, right? It's sort of cut off, but we see visits to up to 10 million URLs. And we see those website visits from hundreds of millions of users. But any one user, as you can imagine, has only visited a small subset of those total possible 10 million URLs. So we have a very sparse, a very large categorical feature space. But it gets even worse when we're modeling survey data because we only have thousands of devices that responded to the survey, and we still see many visits to many URLs. So we still have a sparse feature space, but we have very few devices that responded to the survey. So we really need a way to reduce the dimension of our feature space. So that's what I'm going to talk about today: how we reduced the dimensionality of our feature space. And when thinking of how to do this, we turned to natural language processing. We looked at research performed in natural language processing because NLP data has similarities to ours. So NLP data consists of sentences of words, whereas our data, a small snippet is shown here, consists of sequences of websites visited by devices. Both are high-dimensional categorical feature spaces. So word-to-vec, you probably all know about, is a technique used in NLP. It's useful, it's popular. It takes text features, takes words, and it embeds them such that similar words used in similar contexts are embedded close to each other in embedding space, and therefore converting the categorical features into dense numerical features. So if we can take our sparse categorical feature space, and if we can learn embeddings for each of our URLs, we can convert our feature space into a rich, dense numerical feature space. So that's what we did. We took word2vec and we used it to train embeddings for URLs. So we can train the word2vec neural network to predict a context URL given a target URL. We define context URLs to be URLs visited either before or after in sequence, visited in sequence before or after a target URL. So in this, So in this example, a user has visited these URLs in sequence. We're feeding the network we're predicting from the context URL of the context URLs are hairstyle.com and pophaircuts.com, and the target URL is shorthairstyles.co. There is a dictionary that defines a one-to-one mapping between each URL we are training and embedding for and a row in the embedding matrix. So in this example, we're learning embeddings for 50,000 URLs. So our embeddings are dimension 128. So we have an embedding matrix that's 50,000 by 128. So this works quite well. So to get this to work well, we trained with the browsing history of all devices seen in a 2-week time period, which turned out to be the browsing history of, over 400 million users. And that turned out to be a sequence of over 15 billion site visits. And a portion of the data is shown here just to show that many URLs visited in sequence have nothing to do with each other. There's a lot of noise in this data, but by training the neural network over these 15 billion, the sequence of 15 billion site visits, it's able to learn patterns in the data and embed URLs about similar content next to each other. So we can visualize the embeddings in 2 dimensions using t-SNE. We can then cluster the embeddings, shown here by rotating color palette. And we can zoom in on a cluster. We're zooming in on this cluster. And this cluster contains all sorts of URLs related to travel research. So it seems to work. But we found limitations with this method. So I just showed you how we learned embeddings with 50,000 URLs. But if you remember, we really want to embed up to 10 million URLs. And we want to be able to do this with a network that has a manageable number of parameters. Also, Word2Vec requires a pre-calculation of a dictionary of the URLs you wish to embed. And we're receiving, as I said, 1.5 billion website visits a day. New URLs pop up all the time. They disappear. We don't want to be recalculating our dictionary and retraining our network every day, especially because it takes like 2 weeks to train it well on 50,000 URLs. So we wanted to find a way to train our network with using online learning. That's it. Sorry, that's not the order I was expecting. But OK, so in looking for ways to overcome these limitations, we found this paper. So this paper was published in NIPS in 2017. It's called Hash Embeddings for Efficient Word Representations. And the authors proposed a technique to learn many URLs with fewer parameters by using a trick involving hash functions. And also, they removed the need for a pre-calculated dictionary. So this seemed to solve all our needs, so we decided to try to implement it. First, I'm going to show how it works with a dictionary. So I'm going to show how it's able to learn embeddings for many URLs with fewer parameters than Word2Vec. So the way it works is like this. So we have a URL that we want to embed, and this example is coles.com. Coles.com has a position in the dictionary, which is M, and M indexes this new matrix, which is called the importance parameter matrix. And M is also hashed by two hash functions, H1 and H2, to get 2 more indices, which index the embedding matrix. So the two rows of the embedding matrix are shown here, BI and BJ. We then use a convolution layer and take a linear combination of these embedding matrix using weights in row M of our importance parameter matrix to get the final embedding vector, which is labeled hash embedding here. The rest of the network structure is the same as Word2Vec. So the reason this is able to learn more embeddings with fewer parameters is that we can have a very large dictionary, meaning that this matrix will be very tall, but the embedding matrix is only k by 128, and k is a parameter that can be tuned. So the embedding matrix, the size of the embedding matrix no longer has to be the size of your dictionary, right? So this is a graph to compare the number of parameters needed to train Word2Vec here on the left, and hash embeddings with 3 different values for the k parameter, As you can see, we can train 10 million URLs with fewer parameters, but we have to tune this k parameter for performance, right? So how did we do that? We wanted a quick and easy way to experiment with the performance of training these embeddings. As I said before, they take a long time to train to completion, so we didn't want to train a bunch of different methods of training these embeddings and wait till completion and then put them in our models and look at performance of our models. That would just reduce the amount of experimentation we could do. So we came up with this quick metric. What we did was we took what I'm calling here a ground truth embedding. We had our word-to-vec embedding that we trained for 50 URLs over 2 weeks, and we were very confident in the results. We then clustered those embeddings, and so we had cluster labels for each URL. We then used those cluster labels and the silhouette score and measured, with each test embedding that we wanted to test, we measured how those new embeddings converged to our ground truth embedding clustering. So this metric is not perfect, but it works well. We can see how embeddings are converging to what we believe to be the ground truth over time as they train. And so here's an example of using that metric. I'm showing you the same plot again. And on the right, I'm showing the silhouette score for the 3 different values of k shown here. So in blue, you can see how the silhouette score as the hash embeddings train, how the silhouette score increases as the hash embeddings train when using k equals 50,000. We can then increase k to 250,000. You can see that the silhouette score increases, but increasing it further to 1 million doesn't seem to bring any increase in performance. So we took that to indicate that we can use k equals 250,000 to get the optimal performance from our hash embedding network. So I've just shown you how we can train the hash embeddings to learn more unique, to learn embeddings for more unique URLs with fewer parameters. But I haven't yet told you how we can train them with online learning. So I'm going to do that now. So it's very similar. All you have to do is you replace your dictionary by a hash function. So the hash function, so you hash calls.com and you get m. M is what you index the importance parameters with, and then m gets hashed by 2 further hash functions. The rest of the network is the same. The reason this works with this network structure but doesn't work with word2vec is that in order to avoid collisions, you need to have a huge hash space. So in this network structure, you can have your huge hash space because that only defines the size of this matrix, which is whatever n by 2, and you can still tune k, right? So then I can use the silhouette score again to compare performance of embeddings trained online to performance of embeddings trained in batch. So in orange, we have our word2vec batch trained embeddings, and then in green, we have the hash online embeddings. They seem to train faster and perform equivalently. So that gave us confidence that this method works. So we train our embeddings using TensorFlow. We monitor the training using TensorBoard. This is a screenshot of TensorBoard just for fun. You can see, again, the embeddings projected into 2 dimensions. You can choose a URL. Here, Cruise Law News. On the side, it shows you all the closest URLs in embedding space to Cruise Law News. You can see there are all sorts of websites about cruises. We can select another URL. This is Subaru, Outback, and you can see all the other URLs are about tires and cars. And another URL, this is iGeek's blog, and the closest URLs are all sorts of websites related to Apple products. And finally, there's a website called hypebeast.com, and it's closest to other websites about sneakers. So it seems to work well. So we can learn embeddings, we can train our embeddings online, we can learn embeddings for all the URLs we see in our data stream. And so how do we use these embeddings to model our users? As I said before, we want to reduce our dimensionality. We have this large space, we want to bring it down to this small space. So how do we do that? We have, for each user in our system, we collect their website visitation history. So each user has seen a bunch of websites. Each website has an embedding, therefore it has a point in embedding space. So what we need to do is find a way to combine these points to give each user a point in the embedding space. And the technique that is easy and seems to work surprisingly well, is to simply take the average. So that's what we did. So now all users in our system have a point in embedding space. So then we can build models. So in order to understand how well our embeddings performed as features, we did this little experiment. We took 40 of the standard models we build in our daily system, and we took a training data set of 1 million examples. We then sampled from this training data set, smaller training data sets, so that we could sort of simulate when we had less data available to us. Each box plot here shows the distribution of the % gain in AUC when using embedding features compared to sparse website visit features. And each of these boxes, the training data set is getting smaller. So on the left, you have 100% of the data of the 1 million samples, and on the right, you have 0.1%, so only about 1,000 training examples. So looking at this box plot here, you can see that embedding features perform about the same as sparse web visitation features when you have a lot of data. So usually the models we build have this much data or more. But then if you go down to the sort of number of samples we use when we're modeling survey responders, you can see that the embedding features way outperform the sparse web visitation features. So that gave us confidence that that what we're doing makes sense. So I've just told you how we can build this reduced dimensional feature space, how it seems to perform well on small, when building models with a small number of devices. And I'm going to show you a quick example of how we worked with a survey company and actually put these embeddings to work. So we worked with a survey company that was working with an ice cream brand, and the survey company had administered a survey. We weren't told what the questions were, but the survey company had then built models to predict which of their survey responders were most likely to be influenced by advertising for an ice cream company. So then they passed us the devices. They passed us 5,000 devices, and 500 of those for which they had predicted these devices would be influenced by advertising. And what they wanted us to do was to build models to predict, to be able to reproduce their predictions of the high scoring respondents, so that we could then use these models on our device universe and build segments of devices that the ice cream brand could then go and show ads to, right? So we did that. We experimented with 3 different feature spaces. The embedding features are shown in blue. And then in orange, we have the sparse features. And in green was another experiment we were doing about clusters of website. Instead of visits to a single website, visit to a cluster of websites. And embedding features outperformed all the rest. And actually caused us to be the highest performing partners that the survey company tested. They did a big test with a bunch of different companies. And so in the end, we won the business. OK, thank you. That's it.
With treating sequence of visits as kind of a stack to work back, did you consider looking at the session, right? Because within the session, websites kind of more randomly.
Right. So that's sort of what we do when we feed the data into the model. We see the data and we see like the visits in real time, right? So we collect them in a buffer, and then we feed them into the model. And so if enough time has expired, the buffer goes away, so it doesn't.
Can you detail a little bit more about the selection of the ground truth clusters and kind of how you guys selected those for models?
So the first time we did this, we used like Word2Vec with like the first part that I presented about using 50 URLs and Word2Vec. And we trained that for a really, really long time. And then we clustered with basically with k-means. It's very easy to cluster these things. And so then what we wanted to do for a different part of the business was to label the clusters to have sort of like groups of websites that were about cooking or fishing or whatever. And so we manually, was like a team effort throughout the whole company, went through the whole clustering and labeled and validated it. So it was very sort of hand curated.
Did you look at the position of
For what?
When you only have to do one website, one page view.
You have to see at least two, right, from a user for.
Okay, so you feature all that.
Yeah.
Do you like for like time marketing or like stats engineering some of the features, or you just focusing on the
You mean with the once we've had the embeddings or before we've before? I think the question is what feature engineering did we do before we turned to learning embeddings, right? So, so my company has been building these models for years, and it's actually surprising how hard it is to get them to perform better than with the sparse, with no feature engineering. And so we have done things with recency, like we have like two versions of a visit. One, you visited last week. The other, you visited sometime ever in your life. So things like this seem to work well, but beyond that, we weren't able we haven't been able to do much feature engineering that worked better than the sparse features.
survey data as the input, or looking at other options both?
So survey data is a relatively new application for us. Most of the models we build we build models for our clients that want to do a digital advertising campaign. So they put pixels on their website, and they tell us who bought their product online, and then we build models like that. So usually we work with much larger data sets.
What tools and frameworks did you use to implement all this? And do you have any lessons from that process?
We used TensorFlow and TensorBoard, like I said. So I wasn't the one, so I didn't implement the production version, but so I don't know if I can speak so well to that, but I think it was pretty simple to get it to with the hash embeddings, we were able to implement it in production. Before that, it was not practical to do it.
It's not a question about the actual input data, so you're using just like the like top-level domain stuff and look at other data or like lower level like
So we do, now that we have this hash embedding, we can if there's a full, we don't embed all full URLs because that would be too much, but if there's a particular full URL that's interesting or a topic that's interesting, then we can just add them into the data. So we do embed some full URLs.
What was the next step for you for this project?
I think the next steps for the project are to find different ways to use these embeddings. This is one sort of use case, but how to incorporate them into our standard models and different ways to engineer features from them. Like maybe we can use them to engineer recency features and other things like that. Oh, something else we're doing with them is we're building contextual models. So, as the world goes forward, less and less people want to be tracked around the internet. So we are building like cookie-free models. So we can use these embeddings to do that really well, because basically the embedding is encoding what that website is about. So we can take the embedding and other information we have at bid time and build contextual models.